Our next speaker is Rémi Jaoui, who will speak about integration in finite terms and exponentially algebraic functions.
Thank you for the introduction. Can you hear me? And thank you for the invitation. It's a pleasure to be here, and especially to talk on this day dedicated to Zoe. So just to say a few words, so in contrast with Dave and Françoise, I didn't meet Zoe when she was a PhD student, but I met her when I was a PhD student. And she's always been very influential for me, both on the kind of object in mathematics I decided to study and also on the way I'm trying to do mathematics. And she was always a model for that. And for example, something that she created and organized for many years in Paris is the Geometric and Model Theory Seminar. And when I was a PhD student in model theory with all the other PhD students, we were always going there, and it's a place where we all learned so much model theory thanks to her. And yes, and that I was also very lucky that she was always very interested in the things I was doing. She always gave me a lot of support, and I'm very thankful for that. And when the year passed, then we developed a relationship outside of mathematics too. She knows my wife Ula very well. She met my daughter too. And so I will miss her a lot. Okay, so this talk is about integration in finite terms and exponentially algebraic functions. And so I gave this talk in this geometry and model theory seminar in October, and so I was there still to see the talk. So the basic problem I want to consider is the following problem. So we are going to consider an ominimal structure. So we are going to consider a particular one, the structure that we denote RE. So this is how Van den Dries calls it. So you take the ring language, you also have the order, and you had the restricted complex exponential function. Okay, and I will call this structure the structure of restricted elementary function. Okay, and the basic problems I want to talk about, there's somehow two different ways of formulating it. First, you start with, so given an algebraic differential equation, okay, can you find an exponentially algebraic solution? Okay, and so what do I mean by an exponentially algebraic solution? I mean a solution, an holomorphic solution. So even if it looks I'm working in a real setup, I'm really thinking about holomorphic solution. So an holomorphic solution which is definable in this structure. Okay. The second type of problem, they are somehow just a similar problem. The second one is So I'm not asking about, I don't give you the open set where the solution should be defined. You're allowed to shrink the open set as much as you want. Okay, so I'm not telling you on this domain, can you find a solution? I give you the differential equation, okay, and I ask you, can you find a solution? Yes, in one variable, you can also ask for systems, but yes, let's say in one variable. Okay, and the second problem, which is similar, is that now you're given solutions y1, yn of algebraic differential equation. Okay, and you want to see if there exists a non-trivial relation between them. And so does there exist? Okay, a non-trivial exponentially, do they satisfy? Do they satisfy a non-trivial exponentially algebraic relation? Okay, can you find a function that vanishes at these two functions and is not identically zero and which is definable in your structure? Okay, are the two problems clear?
Exponential algebraic has two meanings in 1 and 2 different meanings. Is that right?
Yes. So one theorem is that this is the same meaning. Yeah. So if you take, okay, if you don't take the restricted exponential, if you take R and semi-algebraic geometry, if you don't take the exponentially algebraic function, so the first problem is just if you replace by R semi-algebraic, the first problem is finding the algebraic relation. And the second problem is finding the algebraic solutions. Okay, and the second problem is finding the algebraic relations. Okay. So in this case, we have various tools in differential algebra, not to fully answer this problem, but to answer meaningful thing about these problems. And so my goal will be to describe extension of the differential algebraic techniques in the algebraic case to study the exponential algebraic case. Okay, it's something that is quite natural to do. Okay. So before explaining what we're doing, let me explain a bit on history of this problem. Okay, and the classical framework, it's based on not on the full class of functions that are definable in this structure, but on a subclass. Okay, so the classical, which is called problem of integration in finite terms. Okay, which was studied by Abel and Neuville. I will give you some information soon. Is about the subclass of elementary functions. Okay, and so what are the elementary functions? They are analytic branches okay, of the function of functions built by composition. Okay, so you're allowed to three kind of building tools: the branches of the logarithm of complex log, the exponential function, and arbitrary algebraic functions. Okay. And the first result that I want to present is from Neuville from 1837. And it tells you that not all functions definable in this structure are actually elementary functions. And so what you will write is that the equation, the solutions of the equations so this one is what is called Lambert equation, okay, and the second one is called Kepler equation, so W minus sine of W is equal to Z. So if you recognize this is the equation that is related for an ellipse, the mean anomaly to the eccentric anomaly in classical mechanics. So these are both equations that were written before the 19th century. And so the solution of this equation, they are not elementary functions. Yeah, the variable, so the solutions W of Z. Yeah, the unknown we are looking for is W, and Z is the variable. So for example, this one, so this one is Lambert function. You can write an explicit power series expansion at 0 of a solution of this function, and Liouville's result tells you that this is not an elementary function. But if you look at these functions, okay, what Liouville says, okay, is that, well, they are still implicitly elementary functions. Okay, Liouville calls them implicitly elementary function. Okay, and so what does that mean is that you can reach them from the class of elementary function by using the implicit function theorem. Okay, and the first idea of this problem of exponential algebraicity that I'm going to give you here, it's a fact which was proved by Wilkie, 2006. Okay, which tells you that indeed this is really the class that Liouville calls the class of implicitly elementary functions. This is really the class of exponentially algebraic functions, those which are definable in the structure. Okay, so every holomorphic function which is definable in RRE. Okay, and this is valid for much more general, for general or minimal structures, is implicitly okay, so except that there's a little catch, is after restriction to some open set. Some open subset. Okay, and so Anand asked me immediately if I was caring about the open set of definition. Okay, so this is one reason why I cannot care about the open set of definition, because I'm new to get this thing. And anyway, to do differential algebra, you never have any control on the open set of definitions of your object. Okay, so you can really think about this problem as asking you, I give you a function, okay, so I prescribe you the function by give you the algebraic differential equation. Can you say if it can be implicitly defined using the class of elementary functions? Okay, this is a naive formulation which goes back to the work of Liouville. Okay, so the second result of Liouville I want to talk about, and I will phrase it in a slightly provocative form. So actually, it precedes the result that I wrote here. Okay, it's the first result of exponential algebra of exponential transcendence. Is that the elliptic integral, the indefinite elliptic integral. Okay, so you take, I wrote it Sn of z, which is just you take the antiderivative of this integral for a cube. So you assume that the thing is not trivial. Okay, is exponentially algebraic. Is exponentially transcendental. Makes sense? And so the proof of this result that I attributed to Liouville, so actually you can find this proof that I'm going to write down in the book that Reed wrote on the problem of integration in finite terms in 1948. Okay, where he says that everything he proves, Liouville knows. Okay, that's why I attributed to Liouville above. And so the first step is a step that is somehow the one that is the most well known, is to show that this function is not an elementary function. Okay, and this is how Liouville phrased mostly his result. But now, how do you show that these functions, which are actually quite natural, right? They appear in the solutions of many problems. They were written independently, not for the purpose of being counterexample, but for their own interest, that this implicitly elementary functions. How do you show that this is actually not implicitly elementary? And then the second part, okay, is that there's actually something that a few years before, okay, Abel stated, or Abel claimed, that if the indefinite integral of an algebraic function is exponentially algebraic, okay, then it is elementary. Okay, and so Reed proves so Reed gives a proof. Okay, and for this reason, so it is unknown to me if Abel was, I mean, if Liouville was aware of this claim of Abel. So we don't have the proof that Abel was giving of this statement, but there seems to be something that about this strategy. So that's the thing I want to talk about. And the third thing I want to say is that during the 70s, so the 1970s, okay, there were many progress, so many progress on the problem of integration in finite terms, on this problem, on one. Okay, and in connection with Axe proof, of the actional theorem. Okay, and it takes the form, so you can find, so important names are Rosenlicht, that we already saw in the talk of Dave this morning, and Rich, okay, Bronstein. Okay, I cannot write all the name. In general, there's a great book that has been written recently by Michael Singer and Clemence Rabe, where they summarize everything about the problem of integration in finite terms. Okay, and in particular, this gives you a full decidability result. Decidability result. Okay, for computing integrals, where here you give me an elementary function. Okay, so if you give me explicitly an elementary function, okay, you can determine if the antiderivative is an elementary function or not. Okay, so the first problem I want to talk about is what about the generalization of 2? Okay.
Exponentially algebraic means satisfy an equation of which kind of shape?
So I say that it can be obtained from the class of elementary function using the implicit function theorem. So basic examples are an equation of this form, where you try to solve. So this is an elementary function, okay, of 2 variables. Okay, and you're
Exponentially algebraic. I asked about exponentially algebraic.
yes. So exponentially algebraic will satisfy a functional equation whose defining function is an elementary function. Okay, so typical examples, they were what I wrote here, the W of Z, K of Z. Actually, if you take an equation like that at random, the solution will rarely be, the generic solution will rarely be elementary. Okay. Okay, so we are trying to understand the difference between the class of elementary function and the class of exponentially algebraic function. Okay, and that's the first thing I want to talk about. So for the connection, so for example, when you look, so the paper where Rich publishes is a solution of the problem of integration in finite term. You can see in the acknowledgement, okay, he thanks explicitly Professor James Hacks for his help and advice during writing of this note. Okay, the second part is Rosenlicht, okay, wrote a common paper where he really proved at the same time the actual theorem and actually problems, and how to solve the problem of integration in finite terms, in algebraic terms. And the third possible way to express this connection is that recently, Pilar and Zimmerman have written an article where they give this algorithm for algebraic functions that is solely based on the actual theorem. So you can really say that using the actual theorems, you get the algorithm for deciding if the integral of an algebraic function is elementary or not. So there are strong connections between the two, and in terms of date, so Axe is 71, the paper is 71, and Rich paper on the problem of integration is 70. So it's also at the same time. So the first thing I want to talk about is the generalization of Abel's result. Okay, so this is the simplest thing to explain. So the basic question is, so let's take this function here. Okay, if you open a differential Galois theory book, you will find a proof that this function is not elementary. Okay, so you can do step 1. Okay, can you do step 2? Okay, so is it implicitly elementary? Exponentially algebraic. Okay, that's the basic question I want to give about. So the first thing to note is that it's not a general thing that every time you're solving an algebraic differential equation, the solutions are elementary if and only if the solutions are exponentially algebraic. Okay, so a counterexample to the naive claim. Okay, actually, we saw it already in the talk of Rémi, which is just this equation, the first order equation associated with the Locke-Volterra system. Anyway, so I'm not using the same notation, but you take the differential equation satisfied by the Locke-Volterra system. In that case, the solutions are all exponentially algebraic. Okay, but they are not elementary functions. Okay, so it's not the case that every time you take a differential equation, if the solutions are exponentially algebraic, then you can deduce that they are elementary. Okay, it was the case for this elliptic integral, or for the integral of algebraic function. So how do you distinguish between this and this? Okay, so this is the first theorem I'm going to explain. I need to state. One. Okay, with which is joint work with Jonathan. It says the following thing. It says that if you take E, consider an algebraic ODE. Okay, so any algebraic differential equation, such as this one, okay, and whose coefficients, where coefficients are elementary functions. Okay, I'm assuming that my coefficient, they are not necessarily algebraic functions. Okay, I'm allowing in my coefficient to have sine z, e to the power z, these kind of things in the coefficients. Okay, so if, and assume that the equation E is internal constant. Okay, this is the condition that Christine explained in her talk. Okay, so it means that from finitely many solutions of the equation, you can generate any other solutions as an algebraic combination of these particular solutions and constants. Okay, so if it is, then you have Abel's claim. If y is an exponentially algebraic solution, then y is elementary. Okay. So essentially, it means that as long as you deal with equations that are internal to the constant, okay, and this equation here, this will satisfy y prime is equal to e to the power minus z squared. Okay, the coefficient is an elementary function, but this is just a simple integration. Okay, this is internal to the constant. You can apply Weyl claims, you can apply Abel claims to deduce that the solution is elementary if and only if it's exponentially algebraic.
This context, you have to re-installation, you work with some, essentially different input streams.
So, yeah. Yes, I'm working in. So here, why? Right now, I only have defined exponentially algebraic for holomorphic solution. So you have to think at y as an holomorphic solution. But indeed, you will be able to replace y by an element of a differentially closed field by defining what this means. You still have to define what this means in a differentially closed field. Other questions? Okay, so there's a corollary that I particularly like. So you can do many, because there's a decision procedure, you can do many functions with this thing. But there's one that I particularly like, a way to phrase a corollary of this theorem. Okay, because it was essentially accessible to Weyl, it's to say that consider the equation of the pendulum. Okay. So which is theta double prime plus omega square sine theta is equal to 0. Okay, I'm going to assume that omega is a non-zero complex number. You can restrict to real numbers if you want. Okay, so the question is, what are the exponentially algebraic solution of the equation of the pendulum? Okay, and the exponentially algebraic solution are precisely the solutions with energy. So you have an energy associated to this equation, square plus omega square cos theta. Okay, this is the energy of the particle. It's preserved over the movement. And the exponentially algebraic solution, they are precisely the one with energy plus or minus omega square. Okay, so if you think about the phase portrait of the pendulum, although it's a real picture, and this theorem describes the holomorphic solution. Okay, if you think about the real picture, okay, so the singular point, they are the zeros of the stationary point of the system, they are the zeros of the sine function. Okay, and you have this, if you have systems with not enough energy, they go around your equilibrium position. And if you have systems with enough energy, they go infinitely many times. Okay, so you have in the middle these homoclinic orbits that distinguish the one that oscillates from the one that goes infinitely many times. Okay, and the only one that are exponentially algebraic, they are this one. I mean, you see them in general on the equation of the pendulum. Okay, they are this homoclinic orbit that separates the bounded one from the unbounded ones. And in that case, it's well known that you can write them explicitly, okay, using elementary functions. Okay, so how this corollary is proved? You see that the equation I'm starting with is not even algebraic. Okay, here the sign appears, but it's not like here where it was appearing applied to the variable. Here it's a coefficient. Here it's even applied to the variable. So what is the trick? The trick is to set u is equal to cos theta over 2. Okay, and if you take u is equal to cos theta over 2, let me get the formula correct. Okay, and you take, if theta is a solution with energy h0, then you can compute that du over dz square is equal to omega square 1 minus u square minus omega square minus h0 divided by 2 omega square. Okay, so for those who know how to describe this kind of equations, okay, so what does that mean? It means that u, okay, so theta doesn't, I mean, the equation I wrote for theta was not algebraic, although theta does satisfy algebraic differential equation too. Okay, but here the equation satisfied by u is an autonomous equation of order 2. And this one is algebraic. Okay, and what this equation tells you, okay, is that this equation, so the equation, the order 2 equation satisfied by u has a rational first integral. This rational first integral, this is the conservation of energy. And the fibers of these rational integrals, they are a family, a non-isotrivial family of elliptic curves. And on each of these elliptic curves, the equation behaves like a translation invariant vector field on the elliptic curve. Okay, and using this, you can prove from this that actually this is not elementary. Another way is to apply Liouville result. You can just apply Liouville's result. Okay, and let me just say something that, okay, so the fact that we have modified theta and u by a cosine, if you look problem of algebraicity, if you're looking for the algebraic solution, okay, you're changing your problem when you're replacing theta by u. Okay, but the fact that we are working with exponentially algebraic solution and exponentially algebraic relation, it makes that this distinction is not, I mean, you can replace theta by u everywhere. Okay, proving that u is exponentially transcendental is the same as proving that theta is exponentially transcendental.
this equation is analyzable but not internal?
This equation is too, no, so it's not the problem. No, so you could, so the theorem is also true with equations that are analyzable in the constant, but just analyzable, I like it better for types than for equations. Okay, but it is not, no, the problem, so we are going to see, so the short proof, okay, the short proof of this result is just to put the square root, okay, and then to write that dz, okay, is equal to du divided by the square root of this thing. Okay, but now this is, when you do that, instead of solving for u in terms of z, you're going to solve for z in terms of u. And so you will get that z is equal to the integral of du divided by a square root, okay, of a quadratic polynomial. So this is an elliptic integral. So now I can apply UV result and say that this object is not elementary. This theorem tells me that it's not even exponentially algebraic. Okay, but now the operations that allows you to move between u and z, okay, to if u of z is an elementary function, then z of u is an elementary function. I mean, is an exponentially algebraic function. You know, it goes, because it's stable by the implicit function theorem, you can do this operation that you can usually not do. Okay, so the second part of my talk is to present you a Galois theoretic proof of this result that avoids doing this computation here. Yes, this is an elliptic equation. That's a log derivative equation on an elliptic curve, and it's an autonomous equation. So it's particularly simple. The solution is internal, yeah. That's why I can apply this that tells me that if the solution is exponentially algebraic, it's the same thing as proving that it's elementary. You know, and I prove that it's not elementary to conclude that it's not exponentially algebraic. Okay. But it's just one example. You can apply the same kind of idea to other example too. And so the second result I want to present is about exponential algebraic independence. So it's true. Yeah. So the result about exponential algebraic independence. So let me start with a basic question. Okay, so we've seen that you can prove that this function here is not an exponentially algebraic function, it's exponentially transcendental. And another case that we've seen is this function here. Okay. So now you can try to compare them. Okay, so the basic question I want to answer is, do they satisfy an exponentially algebraic relation? A non-trivial exponentially algebraic relation. Okay, for example, is this one the exponential of this one? Okay, can you find a relation between these two functions? Okay. And so what I'm going to do is to make a Galois theoretic proof of this result. Okay, and so let's first make a lemma. Okay, so something that that is classical is not to prove that this function satisfies no exponentially algebraic relations, but that they satisfy no algebraic relations. How do you prove that the elliptic integral and the error functions are algebraically independent? Okay, so let me explain the Galois theoretic proof of this result, and then I will explain what we have to change to be able to get tools that study exponential algebraic relation instead of algebraic relations. So the proof, so I'm going to use the model theoretic ways of writing differential Galois theory. So I'm going to write differential Galois theory, but using types instead of formulas. Okay, that's exactly the setup that was used in Stoke. Okay, so the first thing you need is a computation. So how do you? What is the basic computation to show that these are algebraically independent? Is that you can compute the Galois group of these two types. So if I look at the type of Sn of z over C of z, okay, its Galois group is the additive group. Okay, you're just taking an integral and there's no algebraic solution. Okay. Type D, yeah, is for differential. Okay. Yes. Now here, so in the background, I have a differentially closed field. And one with automorphisms. Okay. Yeah. Sure. That's also, but that's true. So the second one is you can compute the second type, the Galois group of the second type. The Galois group of the second type, it is the affine group. Okay. And so the Galois theoretic proof of this result, there's two ingredients. The first one, so you want to prove that these two functions are exponentially algebraically independent. There's two things that you use. The first one, you forget that you use it because it's so natural. Yes, algebraically independent. Yeah. So, and then I'll explain what I have to change in the proof to make exponentially algebraically independent. So the first thing we're using, so this is easy in the algebraic case, but it's actually where the Liouville theory fails, while you have to replace exponentially algebraic, I mean elementary by exponentially algebraic to get good properties, is that the field theoretic algebraic closure okay, is a pre-geometry. Okay, so what does that mean? It means that if you have A, which is algebraic over K and B, and which is not algebraic over K, this is equivalent to say that B, so this is the exchange property that I'm writing here, has the same property. Okay, and this is what makes the transcendent computation goes well, and in particular, so to show that they are algebraically independent, okay, you reduce to two problems. First, you show that the first one is not algebraic, and then you deduce that the second one, I mean, then you show that the second one is not algebraic over the first one. Okay, so this is because you have a pre-geometry that you can actually group things in pieces and reduce to two one-dimensional problems. Okay. So I'm just saying that this is the first ingredient, and then the second ingredient that you're using now. So how do you see what you say here? Is that you have a Galois theoretic characterization of algebraicity. Okay, and that it's a type of type P. It's a differential case. Okay, a type P which is internal to the constant. So let me write it. It's really badly written. So let's say P is equal to, so F is algebraic over K. if and only if, when you look at the Galois group of this type, okay, of the type of f of k, is finite. Okay, here I'm assuming it is internal, assuming internality.
Did you already explain why these two types are internal?
So I just say it's a computation, right? The first one is clear. Okay, the second one you differentiate it twice. Okay, and you will see that it satisfies an order 2 linear differential equation. I mean, the second one, it's clear that it's analyzable. It's not clear that it's internal, but it's actually internal.
You mean it's contained in it? When you say double equal, do you mean contained in, or do you mean actually?
Where?
Do you mean a subgroup of, or do you mean?
No, I mean equal, yeah.
And the first thing when he says, okay.
So I'm saying that using these two things, so what you say, you use B to say, well, this is not finite, so this function here is not algebraic. Okay, the second step of the proof, okay, is now I'm looking at the second function, the error function. Okay, but now I don't want to compute this Galois group over C of Z. I want to compute this Galois group over C of Z Sn of Z. Okay, but the point is, because you have a general group theoretic lemma that characterizes the proper subgroups of these two groups, okay, you can check that actually this is the same. This is still the affine group. Okay, this is just a Boursa lemma. This is just a group theoretic lemma. Okay, we will use the same in the exponential algebraic case.
Order 2.
Yes.
So it couldn't be algebraic over something of order 1. And it's finished.
It has order 2.
It couldn't be algebraic over something of order 1. Which is the first.
Yes. So you have to prove that it's order 2. So
that comes from
the goal, yeah, this is a proof you say is okay too, yeah. So there's many proof of algebraicity. I'm just trying to find the one that I'm going to generalize. Okay, it's not difficult to see that these two functions are algebraically independent over C of Z. Okay, so the first point is that one okay. So the first point, and this is the point that goes wrong in Liouville treatment, is so it's a fact. So the first, so I wrote it 1 or 2, and then this going A. A was adapted to the study of exponential algebraicity okay, by work of my co-author, Jonathan. Okay, so in a paper in 2009, I guess. And so the fact is that every differentially closed field okay, with field of constant C, so with field of constant C, carries a free geometry, okay, that is called exponential algebraic closure, but we put a C to add that C is always in the parameter space, okay, from P of U. P of U. Okay, which has the intended interpretation. Okay, and with the intended interpretation, with the intended interpretation, Okay, so that whenever you have y1, yn, so let me write it like that, that whenever you take functions y1, yn, which are in a field of meromorphic function on an open set U, okay, so when you take objects where you have two notions, you have a notion, okay, given by exponential algebra, and you have a notion coming from this minimal structure. Okay, there's two notions of being exponentially algebraic. A priori, one given abstractly by discrete geometry, and the other one, the one I defined previously. Okay, and the point is that whenever you have that, your elements are independent in the sense of the pre-geometry, if and only if they satisfy no non-trivial exponentially algebraic solution. Of relation. Okay. So we have a well-behaved notion of exponential transcendence degree, okay, that behave exactly like the transcendence degree you're used to do computation with. So what remains is to find the second step. And so the second step is theorem 2, again, is that if you take, so let K be, so let me write like that, the self-sufficient differential field. So we are not able to show it on all differential fields. There's some technical assumption that I'm not going to explain. Okay, okay, and F is an element of a model of DCF0 extending K without new constants. Okay, then so assume that the type it satisfies, okay, is internal to the constant. Okay, then if if F is, so belongs to ECL of CK, okay, with my notation, if F is exponentially algebraic over K, okay, this happens, then the Galois group of the type okay, is linear and abelian by finite. Okay, I haven't defined it. It's a technical condition. Okay, I'm not going to. So it means that we have an analog of the actional theorems over capital K. Okay, I'm not going to if you want, take K is equal to C of Z. The problem is that if you take K is equal to C of Z, you cannot make this proof because here you need to have a second field here. Okay, so there is a there is a small assumption here. I'm not going to describe it, but the point is, if you take something that's exponentially algebraic, then its Galois group is always abelian by finite. You see, the obstruction is smaller than the obstruction in the algebraic case, but you still have a Galois theoretic obstruction for admitting no elementary solutions. Okay, so what I will finish with is that, so you can see that it's not an equivalence. This is already given here. Okay, this function is exponentially transcendental, but its Galois group is the additive group. So it's not an equivalence. Okay, but this function can still be proved to be exponentially algebraic by this using the opposite function. Okay, so you first do the first step like that, but this function is not here, is not exponentially algebraic, was done by Liouville. Okay, and now to prove this, you're going to use the same result because when you add this function, when you compute the Galois group over this field, the Galois group hasn't dropped, and so it's still the affine group. So because the Galois group, so what you use is that if you take G included in GA times affine, okay, so it's Gursa lemma, which projects surjectively on both factors. Okay, then it is everything. Yeah.
Because you're saying that Galois group is like the fiber of
Yes,
G.
and then you say by Galois correspondence, the Galois group is the fiber, so it's still the affine group. Okay, so if you have a simple Galois group, you cannot fork, your Galois group cannot go down by using equations that have Galois groups that do not contain this simple group as somewhere.
So you're saying that the Galois group of the pair.
Yes?
Yeah.
Mhm. Yeah.
Is a subgroup.
Yeah, I'm saying the.
And so that proves independence.
Yes?
Yes.
And you can prove both algebraic independence and exponential algebraic independence by using this, plus the fact that ECL is a pre-geometry. Okay, and you can also apply that for the equation of the pendulum. So I have no time, so I won't state it explicitly. But you can say that, okay, the equation of the pendulum, if you choose your elliptic curves in your fibration of elliptic curves such that they are pairwise, not isogenous, the solution that you get, they will be exponentially algebraically independent. Okay, so in the equation of the pendulus, you already have infinite set of exponentially transcendental functions. And I will stop here.
So, outside of X channel, are you using something else in
Existence. So we are using the theory. So everything can be stated about structural theorems about the theory BE of the blurred exponential.
Yeah, but like if you have an X channel for other functions, right? Because we have lots of those. Are you trying to show that certain functions don't live in the corresponding closure operator?
Yeah. So one possibility is to add elliptic functions, which is very natural to do, but you have to find the right problems that connect. But yeah, so I'm just saying. So this theory is axiomatized by axionual plus existential closeness. So in all situations where you have a functional version of, here we are still using the theorem of Jonathan that says that DCF satisfies axionual, so the theorem of Ax, but also the fact that it satisfies existential closeness. Okay, we are using that in DCF0, you can reduct of this theory is the theory of the blurred complex exponential.
Sure, but that's also true for the J function.
For the J, probably, yeah. For elliptic curve, it's known to. I don't know the J function. So for me, it's not very the elliptic looking. So here the thing is we are looking by integrability by the exponential function. It's something very natural. Adding the elliptic function as well is also something very natural. I don't see why there would be a natural way of studying integrability by the J function. So yeah. So for me, the next case is the case of elliptic functions.
So the action was used precisely in this one exponential closure to this result of development.
So actually is used a bit everywhere, okay? But first of all, in defining the pre-geometry, okay? So you don't have a pre-geometry if you don't have axionual, so everything somehow collapses. And then the techniques that we use, so to prove this, they use things that you can find in the proof of the axionual theorem as stated by Rosenlich. So it's computation using one form.
So again, what is ECL again?
So it's a pre-geometry.
It's on you.
It's on you, yeah. So it's defined by Jonathan.
Differential-Algebraic.
Yes.
What is it?
So it's defined using a pre-dimension, right, which is related to the axial theorem.
So it's word explanation.
Yeah, and then this Fisher's.
It's not ordinary differential algebraic.
No,
No, it's not, it's something else.
it's defined using these pre-dimension techniques, and then you need also that things are self-sufficient when you do these pre-dimension techniques. Okay, and it's really the pre-geometry is constructed like that.
Actually, what is P in that? P of
The part, right? I mean the space of subset of you. Yeah.
So, again, to the end result, sorry, is what? These things are, the end result is these two things are exponentially.
Yes, so it tells you that, so the end results, they are that you have, the first thing, I haven't stated them, but you have decision procedure to decide if certain integral of elementary functions are exponentially algebraic or not, and that you have partial result that allows you to compute exponential algebraic independent statement, which looks like the one that we do in usual algebraic relations. Okay, and they can both be phrased as theorems about the blurred exponential. The first one tells you that something is analyzable in the constant in the blurred exponential if and only if it's elementary. And the second one tells you that all binding groups in this theory are abelian by finite, are linear and abelian by finite. So it's really two theorems about this theory. And this is this theory that describes the class of exponentially algebraic function, not this one.
You say using what's defined, but this notion you didn't define self-destructive or what?
Self-sufficient.
Is it purely field or involves delta?
No, it's purely about the blur, so about BE. It's about the pre-dimension. It's about the pre-dimension. When you make your pre-dimension constructions, you have a pre-dimension. Okay, so if you take L over K, an extension of a differential field, okay, the pre-dimension is the transcendence degree of L over K minus the linear dimension of gamma of L divided by gamma of K, where gamma is a subgroup given by delta of y is equal to delta of x. Okay, so you make a transcendence degree minus a linear dimension of a group. And the way to formulate Axe theorem, it tells you that when K is equal to C of Z, okay, delta of L over C of Z is always positive. And so, exactly, K is self-sufficient if you have this.
It's a function field or shape,
yes, it's a function fiction, really. Yeah,